Hello everyone. Today we will solve lead code number 1101, the earliest moment when everyone become friends. So the problem says that there are n people in a social group labeled from 0 to n minus 1, and we have given the logs in the form of like timestamp, and then the label, basically the person name xi and yi, indicates xi and yi become friends at time t, time at timestamp I. So ith and xi and yi person have become friend in the timestamp, given timestamp. The friendship is symmetric. That means if A is friend of B, then B is a friend of friend with A, right? So it's like bidirectional friendship is there. Return the earliest time for which every person becomes acquainted with every other person. If there is no such earliest time, return minus one. Also, it says that if a person is acquainted with person B, if A is friend with B or A is friend with someone acquainted with B, then it's acquainted. So basically, the thing is, in a social group, there are n number of people who makes friend with other in some time, given time t. For example, if I want to show you here, suppose there are suppose three people we have in a social group A, B, C. Okay, A become friends with B in time t1. Okay, and then B become friends with C in time t2. Okay, and suppose there is one more person who is D. Okay, now A become friends with D in time t3, right? So this, sorry. So this friendship is bidirectional. Like if A becomes friends with D, then D is also friends of A, right? So in this way, like everyone becomes friends of everyone, right? Or like it's acquainted with other friend circle. So we need to return this time t3 because this is the earliest time when everyone becomes the friend. So that's the question we have. We can translate this problem as a graph problem where the nodes are the people, and then edges are the relationship, uh, friendship relationship with the people. And like when the graph is like fully connected, then that is the time when the graph becomes the fully connected, then that would be the time, earliest time that we need, that everyone becomes friend with every other. So we can translate this problem, and also this is bidirectional graph. So so basically it's like unification of the people or the node in the graph. So union and find is the like best algorithm that suits on this requirement. So suppose initially there are n people and all n people are in individual components. So there will be n components initially, and then whenever like they start making friendship, like one other, and then that's how it merges the component, individual separate components. And when everyone becomes friends with everyone, then that time we need to return. So as this friendship is like on the time based, there is time is associated with this relationship. So we need to sort, if we can sort this relation on the time, and if we start like merging the individual components into the single component, and when the component size becomes one, that time if we can find, then I think that would be the answer of this question. And if we are not able to unify all individual components, then I think we there is no earliest such times in that case, so we can return the minus one. So I can use like let me write the union and find template. I'll use weightage quick union with path compression algorithm. So let me first write the parent and size array. For example, parent, we need to compute. Initially, each node will be the parent of itself. So I equal to I for I in range n, and initially the size of the component will be the one because each component will have only one node. So size will be range n. Okay, there is 2n in, remove this. Okay, let me write the find operation. Find x. So in the component tree, for example, suppose we sorted this based on timestamp, and we started unifying the relationship. So how the component tree will look. For example, initially, suppose if I unifying A to B, okay. So suppose A will have child B, and then B is you like we are uh, unifying the component from B to C. Then B will have the child C, like that component tree. So now all three A, B, C belongs to one component, right? So if I have to find, and this is bidirectional relationship, if I have to find the parent of the C, then I need to first ask B and then B will check A, right? So this is one way. If the tree is like large, then we need to have a longest branch. The size, the time to find the parent of this component will be the size or the longest size of this branch, right? So one way would be like we can do the path comparison. Like once, like in the first attempt, we need to find the parent of this C or any node in this branch. And so once we find the parent, then we can compress this path by directly pointing to the parent A. So that is called path compression. So I'll use this algorithm, path compression. So first I'll find, first I'll check whether the X is equal to the parent of X. If the node we are searching the parent, if the parent itself, then simply return the X. Okay. If not, then I'll ask my subordinate to find the root of this component tree by handing over this, my immediate parent. Basically here, sorry, cursor is not so good. So what I'll do that, I'll take my immediate parent. Who is my immediate parent? My immediate parent is this, the current assigned, and then I will ask my subordinate or the next person who is in this recursion to find the root of this component tree, and once it return, I'll just assign into this root x, and then once I find the root of this node in the component tree, then I will compress the path. So basically, how to compress the path? In the original parent dictionary, I'll assign the root x as the node. So now from the next call, we can directly return the root of the component tree of this particular node and then return this root x. Initially, components will be number of nodes into the tree. and then we need to iterate all the connections and then make the like find and do the unification. So for t comma u comma v in connections, uh, and then the first thing we do is make a parent check for each of the component. So suppose I get root u root v value for this find x u and v. So this is one edge or one connection at time t that make a friend. So first we find what is the who is the parent of the component tree where these nodes belongs. Okay, if the parents of both components are not same, then we need to have unification, right? If both are in same component, then we don't need to unify the components, their components. So if ru is not equal to rv, then we need to unify, means both are in different components, right? For example, suppose I have this a and then b, and I want to this is c is in different component. I want to unify. Now the new edge is this, and this one I want to unify, right? So the initially the parent of this component will be c itself, and the parent of this component will be the a itself, right? So this is the new edge we got, and then one when we find the parent of these two components, we got C and A. So we need to unify this. Now, how to unify? One way would be if I make the direct child to B, this C. This is one way. Other way is like I can make this C as a child to A directly, right? So in this case, the in the first approach, like if we make the child to the immediate parent, then what will happen that it will make this tree branch longer, right? And then what will happen? The search time will increase. So instead, like if I make this connection, this C connection with A directly, then my the tree that this form tree will be balanced, means the all the branches will be almost same, right? So that way, like I will have like balanced tree, and then the search operation would be very efficient. So this is called weightage quick union, means based on the weight. And how do we decide? So in the what is the size of this component? One, and this size of this component rooted at is at this tree is two, right? So if my size is small, size of the component is small, then I can just directly plug in to the root to the larger one, so that the unified component tree will have the balance height. So we will use this approach, and then we will write this. So like if size of u, if size of u is smaller than size of basically the root v, then um, then root u component will be the child of this root v, right? So the parent of root u becomes the root v. Now I'm directly connecting this root u to the root v. Now the size of the root v increases by size of root u. So size is the number of nodes in the component tree that this particular nodes u and v belongs to. Okay, else it will be completely opposite. So here it will be v, and here it will be u. Now after this unification, uh, the component size decreases by one, right? Because now two separate component we unified, so now the size has reduced by one. Okay, and when the component size becomes one, right, then we need to return the time. So this is the time which we are iterating, that time we need to return, right? And then uh, if we are not able to find or unify all the separate component into one, then it's not possible to form the one single social group. So in that case we will return minus one. Okay, so basically this is the general template, except this line. Uh, this is the general template for union and find. And to solve this, I have added just this part. And also we need to sort these connections because we need to process or unify the relation based on time. Okay, so yeah, that's it. Let's let me check. Let me do the cosmetic check. So I think this is good. Let me run this. For, okay, I okay. If x equal to parent of x, now parent of x becomes the root x. Yeah, this we need to return the root x. Okay, let me submit to see whether it passes all the test cases. Yeah, it passed all the test cases. Okay, now let's see what is the time and space complexity. So here I'm using weighted quick union with path compression. So for the first call, for the first parent search, it will take the size I mean the branch length of the branch of the component tree, and from the next call it will be O1 search because I'm compressing the path. So if you do the amortized calculation, that becomes the constant time. Here I'm iterating all the connections. So suppose n is number of nodes, n is number of nodes, and m is edges. Then this is OM time, right? This takes order of m edges because I'm iterating all the edges, and this is constant. Find is like this basically o five operations it takes. After five operations, it becomes the constant. So we can say that this is O1 time, and these are all are the constant operation. Here it takes this is On number of nodes, and this is also number of nodes. So total time complexity becomes how much? On plus On. And space complexity. And also, like I'm doing the sorting. So this is like sorting on the edges. So m log m. So this n plus m plus m log m. Uh, so this is the total time complexity and the space. So I'm using only parent dictionary and the size dictionary, and the size of this both dictionary are number of nodes. So space is like number of nodes n time, and in this like I'm not using any other space than this. So this is the overall space complexity and time complexity. Yeah, thank you.